Hey guys, welcome to AlgoYogi, and we are on our algoyogi.io page, practice page. We have already solved Inorder traversal. We're going to solve Preorder traversal today. So let's go to the problem. And if you're watching this video, so I assume you already know what a Preorder traversal is. It's just how to implement its recursive and iterative solutions here. So some people, they know how to write the recursive solution, but when it comes to iterative solution, they kind of feel a little shaky. But we just want to be prepared both ways. So before we go into both approaches, let me switch my view here and let's visualize how we will be visiting these nodes in pre-order traversal of our binary tree. So let me switch to the iPad view here. Now, okay, so I've created this small binary tree here. We know the terminology here is root, left child, right child, and the pre-order traversal, I'm sure you know, it's processing the root first, left subtree or left node, and right subtree or right node. Because you can use them, alternatively, left node or left subtree, or right node or right subtree. Now, let's go into the recursive solution first. So what we want to do is when we are calling our main function pre-order traversal, that's the way we want to, that's the way of visiting all the nodes, is we will be calling our function on our root. That's what we have access to right now. So we will be calling on the root our pre-order traversal, but then calling it on root means we want to process that first. So we will print that out. So if I'm calling it on root and if it is not none, then I will print it out. Then I want to process my left subtree. So I'll call my recursive function on left. And beauty of recursion is if you have the right base condition, which is checking if the root is none, and you are processing left and right in the order you want, then use your original algorithm. If you call it on your subtrees, it should give you the right answer. Then if you call it here, then this time this is also a tree. So now this has to be processed just like we processed this one on root when we called here. So process that. This is a root now, although it's left subtree, but it is a root now for this recursive function we have called it on. So that now it's going to process 2. So it will process 2. But on the bigger picture, we know it first processes the root and then it's processing the left child. But just imagine it in a way that this could have more left and right children. So then this is a root itself as well, right? If it could be, but anyway, right now it's not. Then it's going to process 2. It will try calling on left and right, but they're empty. From the base condition, they'll return back to our root, but root is already processed. Now it will call on right child or right subtree. So I think it's very simple if we are doing it recursively. But now let's also see the theory part of implementing it using iterative approach, which is using a stack. And the reason we use stack is we want to store our previous node, because at a time we only have access to the root node, right? So in that case, we will be using our stack, and as we process root, we will add that to our answer, the array that we will be returning. That's the requirement of the problem. Then we will check if we'll have a current node pointer to our root. Now we will process root, so we will add that value to our answer, but we will also add it to our stack. Then we will keep going left because that's the next subtree or node we want to process. So we'll keep going left until it's none. And we come here. we will go to its left, that becomes none. Then we will basically, when we were here, we will also add it to our stack, and then here we go to the left of 2, it's none. Then we pop out of the stack, we pop it, and what we do, we process right part of it, which is also none in this case. So we do nothing, we just go back, and then we are at, we reach we reach here on our stack. Like we're gonna check if our stack is empty or if our current pointer is none. If our stack is non-empty, then we're gonna pop again 1, and then we process right part of it, right side of it. So in this case, we go to 3, and here we will be basically pushing it onto the stack. But while we are pushing it onto the stack, then sorry, we didn't add this value here. We should have added it. But now when we are at 3, when we're pushing it, we'll process it. But then we go to its left, we go to its right. Well, we go to its left, it's not there. We pop it from the stack and then check it's right. It's none, then we don't care. Then we return back and we will return our answer. Let's implement our solution now. I think this will make things very, very clear. First thing, of course, recursive solution, very easy to implement, and I'm sure you know it. Let's make our answer variable just an empty array. Then let's make inner function, which will be preorder, and preorder takes root. And in our recursive solution, we want to have a base condition, otherwise it will become an infinitely called function in itself. It will keep calling itself. So to exit out, we need a base condition. If root is none, then we return. Otherwise, we want to process the root. So answer append root.val. Right? What now? Nothing, just call it on left and right. Call this function on left and call this function on right. And now in our main function, let's just call it on root, and once it's done processing it, we will have our answer ready and we can return our answer. So let's try to run it. I think we could, if you want to see the solution here, you can focus here. So it's running. Let's try to submit it. Voila, voila, it's done. Okay, so now let's move to our, let's just write the time complexity. Which is big of n. N is the number of nodes, and we are visiting every single node. And space complexity is also big of n, because that's the number of times on the stack we are calling the function. So we're calling it on every node. So sometimes some people might say it 1 because they might not realize that stack is also part of the memory, although it's being done by the machine for you. Okay, so let's, this is done, recursive solution is done. Let's comment this out and implement the iterative solution. Now for iterative solution, as I said before, we will have a stack to keep track of the nodes, to keep reference to our root so that we can come back and process the right side later. So let me just send it down so that, and let me focus here. So we will keep a pointer to our current node, which will be root right now. And while we have current node or stack, we want to keep going left. So while cur node, I want to process the root first. So cur node is my root, so I want to process it. So answer dot append, I just want to use the value, so that will be it, but I also want to keep it in my stack, so push it onto my stack. I'm using a normal array, so it's fine if I'm using the append, or in other languages you can do push and pop. So here I will push my current node to my stack, but then I will keep going left. Sorry, current node will be current node dot left. Okay, now let's see, when this will come out of this loop is the condition where it will be pointing to left side of the root node, or any node, the leftmost, the left known empty child, leftmost known empty child. So in that case, when I'm coming out as none out of this loop. My current node is none. But what I really want is, I want to pop out the root back from where I pushed it onto my stack, and then I came to the none section. But I've already processed it. So what I'll be doing is, I'll be just assigning it that value. So my current node would be just stack dot pop. But see, I'm popping out the value, but that is not what I want to process now. I want to process the right side. So I could just here say, instead of saying it, let's just clearly, current node equals to current node dot right. Now this will point to the right side, and right side itself is a tree which need to be processed in this loop. So until we have our current node pointing to a side that is not already processed, which this stack assignment for popping out the value and assigning to a current node being the and assigning it right side to be processed. That should all give our answer. So we'll return our answer. Okay, so let's try to run it. I'll zoom out, and yep, it runs fine. And let's try to submit it. Okay, so this is all good. So let's mark it done. And next problem we will be solving is binary tree post-order traversal, which will also be similar solution. Make use of AlgoYogi.io, this practice page, to track your problems, and the YouTube channel. Please share and subscribe and give it a like. Thank you. See you in the next problem. Bye.